So let's, what we are going to do is this model that we built is going to be useful for, as I said, two things. One is, once we establish the geometry, we're going to use it to do the rendering of the virtual object on top of our interested, let's say, interest of the world. The second one is we are going to also use it to actually track objects and let's say identify, find the things that of interest to us, so that we can actually have this, let's say, tracking and knowledge of where your camera is, so that I can actually do the projection back. So before we move into the details of how we do the tracking, I want to talk about first a little bit about what a 3D transformation means, and then ways to measure it in different ways and generate it also. And then we are going to talk about a little bit how this pinhole camera model is actually modeled in the graphics engine and the various parts of the graphics engine that is of interest to us. And then next week, hopefully, we'll have a 2-hour session where we are going to actually use Unity alongside with at least one specific tracker, Vuforia, to actually build mobile applications, AR applications, camera-based or video augmented see-through based applications. This will be the next week. So it will be probably 2 hours, and try to actually get to that. It may be online. I'm not 100% sure. I'm going to talk to the to one of your former, let's say, classmates here. So she'll be given the kind of the PS. She may do it online or maybe on site. We'll see that in the coming days. What's that? This exactly at the lecture time, but probably a shorter one, and we'll be repeating the lecture or making up for the 3 hours later on as well. So 3D transformation is very simply, we have an idea of, let's say, a coordinate system for our, let's say, object. So we are going to talk about 3 different things when we talk about 3D. So we'll have a camera. This is going to be either our virtual camera or our camera that actually, let's say, our actual camera or whatever. We'll have a bunch of objects in our world, object 1, object 2, and so forth. And most of the time, these objects will have their own coordinate systems. And then we'll have, most probably, another coordinate system that actually ties these objects together in a world coordinate system. And we are interested in mostly the relationship between the world coordinate system and the camera, but at the same time, the relationship between object coordinate systems and the world coordinate systems, or vice versa. Right. So these are going to be important for us. The reason that actually we have multiple objects and they'll have their own coordinate system is because of convenience. So, for example, I'm going to design this object. Let's say I want to track this, or I want to actually augment this. I'm going to build a model for this one, most probably a tessellated model. And I'm going to use a coordinate system for this one. And he's going to do his phone, for example, and he's going to do that modeling in his own coordinate system, a certain choice. And Sari is going to do his own, and maybe, what's her name? Elif is going to do her own, and so forth. Now, these are going to be our base things that we'll have somehow. And then we're going to say, okay, let's actually take this phone and this thing together I want this to be a part of my world. Maybe phone is going to be a virtual one, this is an actual one, or both of them are actual, and then another one on top of that, let's say Elif brings, that will be actually a virtual one. But I need to actually now, this design of the coordinate systems for this will be arbitrarily chosen by the designer, and I need to get them together to put them in a word coordinate system so that they can relate to each other. I cannot actually have their own coordinate system and talk about augmentation, right? So what are the 3D transformations? We have seen what a 3D transformation is. A 3D transformation takes our world point, let's say point in one coordinate system, and applies to a rotation and a translation, and gets it in the second coordinate system, and vice versa. All right. So you can see that this is one way of representing it. This is saying that I take my world point, I do a rotation on it. Okay, this is the first thing, a rotation, followed by a translation. So this is physically means this. My coordinate system is somewhere here. So this is on coordinate system. I take this coordinate system, align it with my world. Let's say this is the coordinate system, its own coordinate system. I align it with world, x and y. Now they are not exactly in the same coordinate system in terms of translation. I take them and put them here with the same coordinate system. So this is one way. Now once I have this one, I can actually go the other way around. I can take P1, and P1 is simply P2 minus T times R transpose. I can go back from an inverse transformation. An inverse transformation involves an R transform because we do it this way. We say R transpose R is identity. This is a property of a rotation matrix. This is orthonormality. It says a rotation matrix will be orthonormal, meaning each row of the rotation matrix is going to be a unit vector, and their cross product or their cross dot product. So if I take the first row and dot product with the second row, they will be orthogonal to each other. So it will be 0. So when you actually do this one, you can easily see that rotation transform times rotation itself will be an identity matrix. So in that case, if I take this guy here and do a simple, let's say, manipulation on this one, if I multiply both sides by R transpose, like this, let's say, let's do it this way. First, do this one, P2 transpose, P2 minus T is, if I take T from both sides, I will have R, P, P1, right? And then if I actually multiply each side by R transpose, like this will go to identity. So P1 will be R transpose times P2 minus T. So you can do an inverse transformation by, now this time, when you go inverse, you do this one, you take this, you translate, and then you do the inverse rotation. So the translation, inverse of the translation is minus. Inverse of the rotation is transport of the rotation. All right, very simple. Okay. But we have to be careful. So when you do the inverse transformation, you have this R transpose, and you do the translation first. You account for the translation first, and then you account for the rotation second. All right. And we know that if you have a transformation in terms of, if this is represented in homogeneous coordinates, then you have your matrix of this form, and the inverse of this matrix is very simply just R transpose minus T, like this. X, Y, Z, and actually there has to be R transpose here. This is what you can. All right, so this is the transformation, and if you take the inverse of this matrix, you'll see that this is the matrix. Now, what you can do is, in this case, in a homogeneous coordinate, you can actually take your, let's call this big transformation, take your transformation and invert your transformation using matrix inversion. So P1, and P1 will be just tau minus P2, and tau minus is going to be very simple. This part of the thing is going to be just R transpose, and this part is going to be minus R transpose T. All right. So how do we represent the rotations? Let's start with the rotation. Translation is easy. Translation is a certain amount of displacement in X, Y, and Z. So there is no magic in there. Whereas rotation is a little bit trickier because rotation is not let's say a linear operation. It's a nonlinear operation. One way of actually, so there are a lot of different ways people have defined rotation. One, for example, is roll, pitch, and yaw. So this comes from, let's say from aviation. If you think about an airplane, okay, for an airplane there are so you have the airplane. This is the right side airplane. So this is, let's say, if you are, where am I? If you are here, you have a direction this way. This is the front direction where the airplane goes towards. And you have, let's say, a plane here. And then that plane perpendicular to this one will have an axis, and then this one will have another axis. Okay. So this is for an airplane, this axis, this cylindrical axis here, the direction of the movement, is called the roll axis. And then there will be a roll angle along this. So an airplane going this way, let's say, I'm not going to be able to do it. If this is the airplane going this way, like this, and it can roll this way. This is one angle of a possible way of actually rotation. This is first rotation. And then the second rotation is it can actually roll or pitch alongside this direction here. So that think about your airplane going this way, and these are the wings and looking at you. So if you actually rotate it this way, you are pitching the airplane. So if you are going this way, for example, pitching down, and you are going this way, pitching up. Right? This is the pitch angle. And then now there is another angle. This is this angle. If your airplane is, let's say, parallel to the world or the Earth, the axis, the gravity axis, and the rotation around the gravity axis is what is called yaw axis, the yaw of the airplane. So now this helps for example, for these people, aviation people, to actually orient themselves a little bit, let's say, easier once they agree upon such a thing. Okay. So there are three rotations about a set of mutually orthogonal axes. Okay, another possibility is you can define an axis of rotation by, you can define a rotation by an arbitrary axis and a rotation around that axis. So instead of actually, so in your world, you can take any axis like this, let's say in this world, and then you define your rotation around that axis. All right. So this would require one unit vector, right? So this is your unit vector. Let's say UVW in world. This is unit vector, and then a rotation around it. And what they usually do is they take this unit vector and this is rotation. Take that rotation, maybe a cosine of that rotation, for example, as a scale of this guy. So theta, amount of the theta could be, let's say, a multiplication of this one. All right. So now you can actually represent this. This is one way of doing that. Is a vector, non-unit vector, which is actually both taking the rotation axis and the rotation amount as part of this. Of course, when the rotation is 0, then you have when the rotation is actually smaller and smaller, then the magnitude of this vector is going to be smaller and smaller. So you might have, let's say, precision issues. You have to be careful with those precision issues. And another possibility is using quaternions. So quaternion is actually a different representation. Hamilton uses in 1840, I guess. So it's a 4-tuple. So you have 4 numbers. So the 4 numbers are you have I, j, k imaginary numbers. So they are let's say their squares are -1, and then you represent your rotation as something like this. So x, y, z, and w, those are the 4 numbers. And you have these type of relationship between your ij's. I times j is k, j times k is I, k times I is j, and so forth. And then your quaternion vector is actually just v is a vector, a unit vector, and w is a scalar. And this is your representation. And this thing has some interesting properties. So if you have a unit quaternion where q is actually the length of q is 1, it represents the normalized rotation around the u-axis by theta angle, and so forth. And then you can actually convert the quaternion to a rotation matrix using this type of a deal, and then multiplying quaternions, multiplying rotations, actually have interesting properties. So if you have 2 rotations represented by a quaternion, and then when you multiply them, you multiply their corresponding things, and you do a cross product, and this is the resulting thing. So you can actually represent this as a multiplication. And you can see that this is associative because of this guy, but not commutative. Right. Now, one of the advantages of quaternions are actually you can actually do a spherical linear interpolation slur. So this will actually allow you to smooth interpolate 2 quaternions as points on a 4D unit sphere. So this will actually lead constant angular velocity along a great circle between 2 points and on a 4D unit sphere. So this is nice because you, especially when you do, let's say, animations, you would want to actually, let's say, interpolate some rotations along 2, let's say 2 waypoints. And there are a lot of support for these type of quaternions, the quaternion operations in many, let's say, in any given graphic system, including Unity. Unity have, let's say, all these quaternion operations available, so you can use them without re-implementing those things by yourself. Now, this is important because you need to understand the quaternions to represent rotations. Otherwise, the rotation matrix itself has 6 degrees of, I mean, even though it has 3 degrees of freedom, it is a 3 by 3 matrix. So this representation is not actually a reasonable representation. If you want to actually do this representation in a, let's say, in a parameters form, you have to have a non-linearities inside. So let's go back to, I mean, this is transformation. So you have to actually associate the let's say one model to, or one coordinate system to another coordinate system using this. Now let's look at how we are going to actually do the graphics. And this is a very simple, let's say, overview. We have a rendering pipeline in any graphic system. We'll start with modeling transformations. So this means that we'll have models. We might have multiple models, and they may be going, let's say, certain movements, going through certain movements. So you need to actually get these in order. So you might have multiple models with their own coordinate systems that comes to a global coordinate system with perhaps motion. And then now you have all these things are going to be managed by model transformations. And then you'll have the illumination. This is the second part. So model is there now. It's in this same coordinate system, hopefully. And now you have illuminations. The illumination is going to be the part where the light is going to be defined, the amount of light and the position of the light and so forth. And then the third part is the viewing transformation. This is where your camera is going to be. Your camera is going to be defined by its location, its let's say viewing angle, and also the field of view. And field of view, for that we have a certain, let's say, parameterization as well. And then the fourth step is going to be clipping. So the clipping is going to be, so assuming that this rendering pipeline is actually doing, let's say, let's call it for the time being a triangular representation of the surface. So you'll have all the triangular representation of your surface in the right coordinate system, including your surface normals. So you'll need a surface represented by individual entities, triangular entities, which are going to be formed by 3 vertices. And then you need also a surface normal indicating where your surface is with respect to, let's say, or where the outside of the surface is. Right? So this can be either represented by a normal, or it can be also reconstructed from the triangle formation process. But usually we'll have the normal. Now, this modeling transformation will be applied to the 3D locations as well as to the surface normal as well. So you have to actually do that. So illumination defines where your light is, okay? And then viewing transformation defines where your camera is looking at this thing. And then clipping is going to be in 2D. If you look at this 2D, so you have it's a triangle here, and you have your camera here, and this is your, let's say, the field of view, and this is your image plane. What will happen is that your triangles, for example, this triangle and this triangle, 2 triangles here, this will be visible by your camera, but this thing is not going to be visible by your camera. Portion of it has to be clipped. So this is going to be this process. So each triangle will be actually going through this clipping process. And at the end, once you actually have the clipping process, clipping process will happen in 3D, and then you'll have the projection. So then this will be projected and rendered in the image, each of these. And then this projection of these locations, of these, let's say, corners, the rest of this is going to be filled by the rasterization process. So you project the corners of the triangle, and then you render inside of the triangle based on the viewing light and also the surface structure as well as the surface normal. And then you display it. So this is the simple rendering pipeline that you need to actually know. Any questions on this? So rasterization is this. So the way that actually the rendering happens is this way. So you take this your triangle, for example. Say, okay, this is my triangle. Let's say that we are going to use for the time being a simple model where let's say the shading model is going to be just flat shading. I'm going to see if I am seeing a pixel, I'm going to actually just render that with that color, whatever the color is. So the way that this triangle in 3D will be during the projection process, it will be projected to the image plane as this. Let's see. First, think of this as a virtual one, but I need to actually display the rest of it like this, right? So inside has to be filled. So the way that rasterization works is, it actually, instead of let's say picking points here and projecting them, which will be quite expensive, the rendering happens actually on the 2D. So once I know the boundary of the triangle, I will actually have these horizontal lines, and I will start the first horizontal line, and actually I start from this part, and move, if you look at, let's say, this way, if these are my pixels, and if this is the line that I am supposed to be drawing, right? So the rasterization says, okay, I will actually go from here to here with a simple algorithm, just by actually saying, okay, this has to be lighted, and then this has to be lighted, this has to be lighted, this has to be lighted, and this has to be lighted, and this has. There are there are very simple algorithms like Bresenham, and these are very efficient algorithms to actually do this rasterization, both lines and inside the triangles. So this is kind of a divide and conquer method to actually make these things very, very simple. So you can see that now in this thing, you have very simple operations. So the operations are, you'll see, you take all your vertices and you project them, for example, or you, let's say, transform them with a rotational translation. And then rasterization is similar. You take your all 2D points and actually say, with a very simple integer arithmetic, you actually just find the right coloring or right, say. So each of these things are very, let's say, similar to SIMD architecture. Single instruction, multiple data. The thing that you are doing is a projection. So projection is a matrix multiplication, that's it. But you have multiple of these data. You have 1 million vertices, 1 million triangles, and so forth. So because of this, people have actually, using this pipeline, people have devised, let's say, graphical processing units. So these are special purpose hardware that actually optimize for this type of right. And GPUs are, of course, now you have to, I mean, you'll have multiple of these cores, many of them, 2,000 of them, for example, and then each will be doing actually the same operation, but on different data. So if you have 2,000 cores and you have, let's say, 2 million triangles, your projection will happen once, and at the same time, you'll be handling, in one cycle, you'll be handling 2,000 of those projections. So 2 million divided by 2,000 will be how many cycles you need to actually spend on this type of projections. Of course, you can do this on CPU as well, but it will be much more expensive to do. So the GPU is, again, is a special hardware. They say it's like display card or whatever, but it's actually called graphic processing unit. So this is why it's optimized for this graphic pipeline, graphic rendering pipeline. Okay, let's see. Now, for this pipeline is followed in, let's say, or used almost the same way in let's say, libraries that we have. So the basic library is the OpenGL. This is Open Graphics Library, and it is actually an implementation of this pipeline, and it has basic stuff related to realize this. So things like, for example, you see a projection, as a projection stack where your projection matrix is going to be actually kept in. And then you'll have a model view that will control the camera's location. And then you'll have, for example, as part of your GL projection, the projection matrix will be, so the way that you can define a projection matrix in OpenGL, for example, is not going to be this model that we had. So this alpha U S U0, alpha V C X U0, and V0 and so forth. So this is not going to be finding an equivalence in OpenGL, for example. You'll see that some other, like Unity, will have some sort of equivalent thing, but the way that, let's say, OpenGL is going to assume this one is going to say, okay, I will define my camera starting from a frustum. Frustum is actually, let's say, a kind of a thing that defines your geometry, something like this, right? And then you define an minimum X, minimum Y, minimum Y, and maximum Y, and then a near and far place where you actually define from a top view, for example, this will be, let's say, your frustum where things are going to actually happen. Meaning a triangle that actually lies inside this frustum is going to be, let's say, displayed, and the right, the ones outside is going to be clipped out. So this is, again, a kind of a tool that reflects, or a library that reflects this pipeline that we discussed just a minute ago. And then you can have a perspective projection on top of it with field of view defined aspect ratio. This will be the aspect ratio that we had here. This will be the difference between these two. And then you can have, again, a near and a far plane, which is your cutoff plane, the volume that is defined by your. You can have orthographic projection. If you don't want to have, let's say, perspective projection, you can easily use GL ortho to define your orthographic projection. But GL projection is actually a matrix. The representation is like any matrix, a 4x4 matrix. So you can use it for different, let's say, you can multiply it by, you can put a multiplication, you can stack them together, a few of them, or you can have, let's say, some model view matrix in front of it that actually precedes the GL, the projection matrix. The Unity thing will cover this a little bit, the tutorial on Unity. We'll talk about the model views, but from Unity's perspective, not OpenGL's perspective. OpenGL is a very low-level library. Unity is a higher-level library that actually is implementing most of these OpenGL stuff, and it actually also gives you an editor and so forth, so that, or an IDE, a development environment, that actually makes this happen. So OpenGL, for example, you can use in C, C++ as a just a simple library, whereas Unity has its own, let's say, it's like it's not a language, but it's like a program where you can actually do some of these things visually, some of these things programmatically. Scripting, and scripting language is going to be a C# for Unity. We'll talk about these a little bit more. The next topic is going to be calibration. I'm done a little bit early, but I'll take a few questions, and we'll resume here for the week. Any questions? So next week we are going to talk about calibration. We are going to say, okay, I have a 3D object here. I have a camera. How do I calibrate? Meaning, what is the rotational translation? And then after this, we are going to say, okay, okay, let's start with this one, and then we'll talk about more about this. So
do you need blueprinting mechanism? Test like something like its own language? Do you need a blueprinting mechanism?
No. Scripting. I mean, so blueprinting can be done visually, but you'll have, let's say, you'll have a programming environment to program things, and that will be C#. But it's not again, it's not a language, it's not a
framework.
It's a framework, it's a platform, it's a program. At the end, it's a program, including some compilers and some, let's say, linkers and so forth. So it's kind of an in-between thing. It's not a language itself, but it's not It's not just a program either, so it actually creates a program for you. Some visual, you can call it maybe visual compiler or something like that. Maybe. So again, we'll be using Unity for graphics needs. And now what happens is that Unity will need to have some support for AR. Two things, camera access and tracking or finding the object, 3D object and image relationship. So for this one, we use, for this support, we'll use Vuforia. And Vuforia is a SDK that has, let's say, plugins for Unity that provides both access to the camera of the thing as well as tracking capability, and it is tied easily to, let's say, the projection matrix of your virtual camera that you'll be using to render things. So it will make your life easy. And you'll see that actually this is going to be done in maybe no coding at all, just associating a few different things in the visual interface of Unity, and you'll be able to actually have a Hello World application right away. But our homework is going to involve a little bit different things. We are going to ask you to explore both model part, so that you can have multiple models moving in the environment. That's the first part, so that we'll want you to make sure that you can handle multiple models and their geometries and so forth. The second one is we want you to use, let's say, some markers to do the augmentation. But during the augmentation, we want to also you to try a little bit interaction with the objects. So this will be the interactive nature of the AR. So we'll ask you to, for example, do object selection and manipulation on your program, the AR program. You'll see the descriptions. So if you know Unity, the homework will take probably a couple of hours. If you don't know Unity, maybe 4 or 5 hours. What's that?
I doubt that.
No, I mean, there are a lot of tutorials. If you start with the tutorials, it's like, but try to learn it, because we'll have one more homework with Unity, and then we'll have also a project that you'll have to be doing as turn project. So that will be mostly on Unity as well. So it's better to learn it now. All right. So if you don't have any questions, let's stop today. I'll see you not next week, but the week after.
Next week, the class will be on the same time, right? Again?
Yes.